We will never reach the nearest star. Not in 1,000 years. Not in 1,000,000. Not with any rocket we could ever build. That sounds impossible to believe. Until you see the numbers. The cruel part is that the nearest star isn't even far by cosmic standards. It's our closest neighbor, and it's still completely out of reach. Even light, the fastest thing that exists, takes over 4 years to get there. If even light takes over 4 years, what chance do we have? Here's the part that should really bother you. The distance isn't the reason we'll never get there. The real problem is what happens the moment you try to solve it honestly. Because every fix creates a worse problem behind it. Let's break down exactly where it falls apart. Voyager 1 has been traveling since 1977, nearly 50 years of uninterrupted flight, making it the most distant human-made object ever launched. It currently sits roughly 24 billion kilometers from Earth. In terms of reaching Proxima Centauri, it has covered approximately 0.02% of the journey. At its current speed of 60,000 kilometers per hour, Voyager 1 would need roughly 73,000 years to arrive. Here is what 73,000 years actually contains. The oldest cave paintings on Earth are around 45,000 years old. Writing was invented 5,000 years ago. Agriculture, cities, science, every empire, every war, every discovery, every written word in human history occupies only a fraction of that journey. And Voyager is already our fastest long-duration spacecraft. So we go faster. That is the only logical move. But faster is where the universe begins pushing back. The fastest object ever built by human hands is the Parker Solar Probe, reaching peak speeds of around 692,000 kilometers per hour by using the sun's gravity as a free accelerator. At that speed, the crossing to Proxima Centauri would still take roughly 6,300 years. And here is the problem buried inside that number. In open interstellar space, there is no star to fall toward. Whatever speed a ship launches with is the speed it keeps, unless it burns fuel to accelerate further, which means carrying that fuel, which means more mass, which means more fuel required to move that mass. The problem compounds before the mission leaves the ground. So, what does physics actually permit as a ceiling? Nothing with mass can reach the speed of light, not because engineering has not caught up, but because the universe will not allow it. Infinite energy would be required. Infinite energy does not exist. But suppose a ship could travel at 99% of light speed. At that velocity, Earth would measure the crossing to Proxima Centauri as approximately 4.3 years. But the crew would experience significantly less, roughly 7 months of subjective travel time, because relativistic time dilation compresses their experience of the journey. This is not a theory. Atomic clocks on fast-moving aircraft have confirmed the effect directly. 7 months to reach another star. For the first time, a number almost sounds workable, which is precisely the moment the next constraint becomes visible. Interstellar space is not a clean vacuum. Between the stars, gas and loose particles drift in what astronomers call the interstellar medium. At 99% of light speed, a single hydrogen atom strikes the hull with energy comparable to a high-powered rifle round. Not occasionally, constantly, every second, for the entire crossing. At these velocities, even microscopic particles become catastrophic hazards. Any shielding capable of absorbing this continuously would need to be extraordinarily dense, which feeds directly back into the fuel equation. Every kilogram of shielding requires additional propellant, which adds mass, which requires more propellant still. And there is a second effect that demands still more shielding. pushing the design even further toward impracticality. As the ship accelerates, incoming light undergoes blue shift, wavelengths compress. Visible starlight ahead shifts upward in energy, first into ultraviolet radiation, then X-rays, then gamma rays. The forward section of the spacecraft becomes bathed in radiation lethal to unprotected biological tissue within minutes. More shielding, more mass, more fuel. The spiral tightens with every proposed fix. And none of this has yet touched what the journey does to the people inside. In weightlessness, bone density decreases at roughly 1 to 2% per month. Muscle mass degrades. Fluid shifts toward the head, affecting vision and cognition. These are measured effects from 6-month missions aboard the International Space Station, where crews return requiring extended rehabilitation. Even 7 months of ship time runs directly into these effects. And throughout that period, chronic particle radiation accumulates in biological tissue, damages DNA, and progressively compromises neurological function in ways that ground-based medicine cannot reach. Then there is isolation. Studies of crews in Antarctic winter stations and long-duration spaceflight simulations consistently show the same pattern. Cognitive performance declines, emotional regulation deteriorates, group dynamics destabilize without external support. In interstellar space, that support becomes physically governed by the speed of light. As the ship moves farther from Earth, every message takes longer to arrive. Halfway to Proxima, a transmission takes roughly 2.1 years to reach home. At arrival, a single word requires more than 4 years to reach anyone who could respond. Whatever breaks, whoever breaks, it is resolved entirely by whoever happens to be aboard. That is a condition no human mission has ever been structured to meet, and it is still not the deepest layer of the problem. Every interstellar mission carries its own version of the same hard boundary. There is a point in the journey, determined by velocity, remaining fuel, and the physics of deceleration, beyond which returning to Earth becomes physically impossible. Not difficult, impossible under the known laws of physics and any propulsion system currently conceivable. The threshold passes silently, somewhere in the dark, determined not by anyone's intention, but by arithmetic. From that point forward, the mission is irreversible, not as a dramatic commitment, but as a quiet consequence of velocity and mass. When Apollo 13 lost an oxygen tank 320,000 kilometers from Earth, 200,000 miles, engineers on the ground had hours to devise a fix. When Mars rovers encounter faults, specialist teams spend days running simulations before sending a single command. That entire structure disappears at interstellar distances. Just a ship, whatever it launched with, and the compounding silence of space growing around it. And there is still the destination itself. Current models suggest Proxima Centauri produces violent radiation flares on a regular basis, events that blast surrounding space with high-energy particles and regularly affect Proxima b, the planet within its habitable zone. Arrival is not the resolution of the problem. In some respects, it may be the beginning of a new one. So here is what the journey to the nearest star actually reveals. The distance itself is not the true obstacle. The distance is the condition under which every other constraint becomes visible, one after another, each one invalidating the solution to the one before it. Speed sufficient to compress the journey into a human lifetime generates particle impacts that threaten the structural integrity of the ship. Shielding sufficient to survive those impacts demands mass, that breaks the fuel equation. Radiation from blue-shifted starlight requires additional protection that compounds the mass problem further. The biology of the crew degrades throughout a journey that medicine cannot reach from the outside. The psychological toll of total isolation accumulates in an environment where no external support exists, and somewhere in the early phase of the mission, before anyone on board has fully absorbed what has happened, the option to turn back disappears without announcement. Each layer does not simply add difficulty. It erases the solution to what came before. Proxima Centauri is 4.24 light-years away, 40 trillion kilometers. In the full span of our galaxy, which stretches roughly 946 quadrillion kilometers across, that gap is almost nothing. A few steps between neighboring houses on a street that extends beyond comprehension. And those few steps, followed honestly through every physical law we currently understand, close off one option after another until what remains is not a mission with a return date, but a one-way passage into silence. The universe did not arrange this to be cruel. It simply built the physics before we arrived. And the physics, followed all the way through, closes the door quietly, long before most people thought to check whether it was open.